We did this yesterday using just the change momentum. We didn't use conservation momentum. So I want to attack this problem with conservation momentum instead. All right? You guys get practice with conservation momentum. Practice. Practice makes perfect, right? Unless you're Allen Iverson. All right. So, a 0.5 kilogram collision car is traveling at 1.3 meters per second when it collides with a 1 kilogram collision car traveling 0.9 meters per second east. After the collision, a 0.5 kilogram collision car has a velocity of 0.3 meters per second. What is the velocity of the other car? Now, when I am doing a problem like this, I need to draw a picture. Okay? If I do not draw a picture, then I get confused. Okay? Kyle, stop playing with collision cars. So, before the collision, I have a 1 kilogram collision car traveling this way at 0.9 meters per second. Right? The reason why I show it that way to the east is if we're looking at a map, right? Washington, D.C. is over here. California's over here. Right? Okay. The other collision car is traveling this way, 0.5 kilograms at 1.3 meters per second west. Right? Does that make sense? Now, besides my picture, I also like to make a list, Anthony. Okay? I need to make a list. If I don't make a list, I get confused. Right? The reason being is this is a conservation of momentum problem. Right? So remember, our conservation of momentum equation was m1 v initial plus m2 v initial equals m1 v final plus m2 v final. That's our conservation momentum equation, right? So I need to know which one's 1, which one's 2, and which velocities are which. Okay, so from my before picture, m1, it doesn't matter which one you call m1. Okay, little hints. If you call it m1, write a 1 next to it. Why? So you don't get confused. So let's call this one 1. So that means m1 is 1 kilogram. And m2 is 0.5 kilograms. Right? Or those 2 next to this one. Okay, so that way I don't get confused. Right? Pictures help. Okay. What's velocity of 1 to start? What's v initial of 1 to start? 0.9. What's v initial of 2 to start? 1.3. Okay. Now with momentums, does velocity matter? Does direction matter? Yeah, these are v's, not because they're speeds, but because they are vectors. They're velocities, right? So direction does matter. The most common mistake by students, Michael, is forgetting a sign. Forgetting which one is negative. All right? These two cars are heading in opposite directions, right? So one velocity has to be negative. So which one's negative? Does it matter?
2.
Does it matter which one's negative? No. Typically you guys call it to the right positive. So we'll stick with that trend, which means that is 1 negative or is 2 negative? 2. Okay. Now, if you think you're going to confuse your velocities, or if you're drawing your list in a straight line, put a little 1 and a little 2 next to your velocity so you don't get confused as well. Okay. Then it talks about after the collision. So guess what I do? Draw an after the collision situation. You don't need to draw the collision. If you want to, that's fine. Okay. So after the collision, here's the 1 kilogram car. Here's the 0.5 kilogram car. They do not change masses. Okay. So after the collision, which way is the 0.5 kilogram car going? Right. So 0.3 meters per second east, right? So this is 0.3 meters per second. Which way is the 1 kilogram car going? We don't know. And we don't know which way it's going. Because it says, what is the velocity of the other car? Okay? So this is where the conservation momentum gets involved. Right? This 0.3 meters per second, that's V2 final, right? Right? Do the masses change? No. And that 0.3, is it positive or negative?
Negative. Wait, positive.
Positive. Okay? So the 0.5 kilogram car changed directions, didn't it? The impulse to the right was so great it made the car change directions. Right? So now we can plug into this equation. We can plug in what we know. So M1 is 1. V initial is 0.9. M2 is 0.5. V initial is negative 1.3. Do not forget the negative. It will really change your problem. Okay? M1 after, it doesn't change. V final we do not know. M2 is still 0.5. The V final is now a positive 0.3. So now we're going to solve that equation to find our final velocity. What's 1 times 0.9? 0.9. Plus 0.5 times negative 1.3. What's that? Negative 0.65. Plus 1 VF. Plus 0.5 times 0.3, which is 0.15. So now we took a really difficult physics problem and turned it into like a middle school math problem. Right? Solve for the variable. Can we do that? Okay. So 9 plus negative 0.65, what's that? 0.25 equals 1 VF plus 0.15. What do I do now? We already started solving. What do I do now?
Minus 0.15.
Thank you. Subtract 0.15 from both sides. So we get 0.1 equals 1 VF. Now, if the mass was anything but 1, we would divide by that, right? Right? But since the mass of that first collision car is 1, we know our final velocity is 0.1 meters per second. Okay. So which way is that car going after the collision? Is this car going left, or is it going right?
Right.
All right, good. It has a positive velocity, which means it's going right. It's just going really slow. Have we seen this before? Yep. Or have your car collides with a lighter car, and this is why. Kyle, I need my collision cars back.
Right there.
What's that,
Why does
Caleb?
it have to be negative 1.3? Why can't it be?
Why does it have to be negative 1.3? Because
Well, I know, like, why is it 1.3 though? Why isn't it?
Because before the collision, they were traveling in opposite directions, right? Before the collision, these cars are traveling in opposite directions. So one is positive and one has to be negative.
I just put the negative 1 V final. I did that
So where'd you put the negative?
with the 1.
With the 1. You put it right here. You put it right here.
Negative V final.
Negative 1 is fine.
No.
After equal sign.
1
So that?
negative
Is that what you're talking about?
Why'd you make that negative?
I don't know. I just made something negative.
Oh, you can't just make something negative. It has to be the right thing. So this initial velocity has to be negative. Okay? And if I solved and got a negative answer here, that means my V final for the other one will be going the other way. Okay? Alright, so the collision cars one more time. We'll be done for the day. Rex's favorite words, right? Done for the day. So, theoretically. Alright. So here I have here are the red and blue car, right? Right, red and blue car. So this one is the one that's traveling east, 1 kilogram. This is 0.5 kilograms, right? I know. Okay. So before the collision, the blue car had a bigger velocity than the red car did, didn't it? No, the red car had a bigger velocity, right? But when I pushed them towards each other, right? Oh, that's perfect. Why couldn't I do that yesterday? When I push them towards each other, oh goodness. Okay, the red car still has a velocity afterwards. Now friction took it away, but it can still have velocity afterwards. What I'm trying to show you is that it's possible for two cars to collide and one car keep going in that direction. Try one more time. See?
Exaggerate it.
Still going.
Like, roll that red
Yeah, I'll knock the blue car off the track. So slow blue car, fast red. Right, keeps going. Okay. You guys see that? So it is possible for two cars to collide and both go in the same direction afterwards. It's also possible with a larger velocity from the smaller car for the red car to go back in that direction too. Does that make sense? Basically, any possible result is anything you can think of is a possible result. Right? Any questions?
Is it possible for them to grow wings and fly away?
No, that'd be improbable, Rex. Is it possible for you to grow wings and fly away?
Theoretically.